Hey everybody, welcome back to chemistry. And so now we're continuing on through chapter 4 where we're looking at a variety of different kinds of chemical reactions. And so the first chemical reactions we were looking at were called ionic reactions. And now the next chemical reactions we're going to be looking at are something called neutralization reactions. But before we get to those kinds of reactions, we have to talk about the reactants of a neutralization reaction. And the reactants are acids and bases. And so first thing I'm going to be doing is talking about acids. And so if you want to read about this in your book, it can be found in section 4.5 and 16.1. So again, let's just talk a little bit about what acids are. So acids are molecules or compounds that when added into water dissociate to produce hydrogen ions. And so to get some idea of what that is about, let me just write out some things here. So what I want to do is kind of understand an acid a little better by comparing it to, say, an ionic salt dissociating in water. So here I'm going to have ionic salt, and so we'll use our favorite, which is sodium chloride. So here is sodium chloride here. And so you probably know that at room temperature and pressure, you usually find sodium chloride, which is table salt, in the solid state. So we'll include a state symbol like that. Okay, and so we can imagine what happens when you add salt to water. What will happen is that the salt crystals dissolve in the water and they release sodium and chlorine ions into the water. So I write here sodium ion here. It's going to be dissolved in the water, so we note the state symbol here of an ion dissolved in water with the aqueous symbol here. And then we have chloride going to be dissolved in the water. Now, if we wanted to, we can just sort of remind ourselves that we're taking these salts and dissolving it into water by putting water over the arrow. Okay, now let's compare that to how an acid dissociates in water. So a common acid, which you probably have heard about, is called hydrochloric acid. And so its formula is HCl. So this is an acid here. Okay, so now HCl will do something similar to sodium chloride. When it hits water, what you'll get is not so much a sodium ion here, but because we have HCl, we'll get a hydrogen ion. And this will be an aqueous solution. And then we'll also get the chloride ion, which will be an aqueous solution. Now, what is the state symbol for HCl? Well, it depends on who you talk to. But for example, what's interesting about HCl, along with all the other hydrogen halides, at room temperature and pressure, they are gases. And so one thing you could do is you could put a G here to indicate that it's in the gaseous state, because in order to create hydrochloric acid, you would have to take the gas and bubble it into water. But usually what chemists do is they sort of pretend that the molecules of HCl just for a moment are in the water, and then they'll dissociate later. And they imagine what the molecules look like in the water. And so again, these are molecules that are in the aqueous state. So usually you'll have chemists that write AQ here. And again, what I'm going to do is to indicate that we have these molecules going into water and dissociating in water. I'll put an H2O here. Okay. Now, one thing you can see is why one of the definitions of an acid is of a molecule that when dissolved in the water dissociates into hydrogen ions. And so here, this is an acid because you're producing hydrogen ions here. And so where do they come from? Well, they came from the hydrogen that's bound to the chlorine. And so one of the things that you'll see in all acids is they'll have some hydrogen in it. Now, sometimes it's going to be one hydrogen, sometimes it's two, sometimes it's three. But usually, to indicate that you're dealing with an acid, most chemists write the H in the formula first to indicate that you're dealing with an acid and that this hydrogen ion can dissociate off the anion and give you the solution of acid. Now we can sort of generalize this, as I've sort of done in the screen here. So we can say general, that maybe an acid molecule might look like this. You have hydrogen bound to some kind of anion here, so we have an A here. And most of the time we think of the acid when going into water will be in aqueous state. And so it goes into water and it always produces a hydrogen ion. And then the ion that's sort of separated from that is the anion. So we need to include that like this. Okay. And so if we wanted to, again, we can just indicate that these acid molecules are dissociating water by putting water over the arrow here. Okay, so now I want to digress for just a second. And so one of the things you'll probably hear chemists do is what they'll do is they'll use the word proton and hydrogen ion interchangeably. So a proton is a hydrogen ion. So let me talk a little bit about why that's the case. So imagine for a moment you have a hydrogen atom. So we're just going to write H like that. And then we're going to compare that to a hydrogen ion. And so hydrogen ion is H with a plus. Now let's go back to the hydrogen atom and imagine what that looks like. And so a hydrogen atom, it has an atomic number 1 that indicates that it has 1 proton, right? So there's 1 proton. So I symbolize that with a plus like that. And then also, if the hydrogen atom is neutral, which it is, it'll have 1 electron. Now, just a note, there are some hydrogen atoms in the population of hydrogen atoms that will have an additional neutron, but most hydrogen atoms out there, like found in water, do not. They're just made of a proton, okay? So anyway, so let me draw a stupid picture of this. Here's the stupid picture. So here's the proton in the middle of the hydrogen atom. And then some distance out, you'll find the electron. It'll be in an area outside of the proton. That area is going to be called an energy level. You'll learn about that in later classes. And so we'll just put the electron here like that. Now, what is a hydrogen ion? Well, a hydrogen ion has a positive charge. And I think one of the things you learn is that the way you create a positively charged ion from a neutral atom is by pulling off an electron. So you don't so much add a proton to get the positive charge. You take a negative charged electron away, and that gives you the atom with the positive charge. So we have here in a hydrogen ion here, looks a little bit different. It is just 1 proton, and that's it. There's no electrons at all, so I'll write no electrons. And so it kind of looks like this. We just have a hydrogen ion here. It just looks like this. It's just a bare proton, that's it. So you can see the hydrogen ions are a lot smaller than the hydrogen atoms here. So just be aware that a hydrogen ion is often called a proton. Okay, so let's move on. Okay, so I have some examples of other acids here. So there's the one I just went over. And then here is another acid. It's called nitric acid. And so nitric acid, when added to water, will dissociate to produce hydrogen ions. And then the NO3 minus you see there, you might remember that's a nitrate anion. And here's another example. This is sulfuric acid. Its formula is H2SO4. And so H2SO4 sulfuric acid is a little different. When it goes into water, it tends to lose 2 protons. And so you can see there's 2H plus there. And then what's left is the sulfate ion, which is SO4 2-. Okay, so I just want to point out that all these acid equations that I have written are consistent with the so-called Arrhenius definition of an acid, which is a molecule when added into water dissociates to form hydrogen ions or protons. Now, one important thing that you sort of need to understand is that when we add an acid to water, this is not exactly what happens. So with the Arrhenius definition, Arrhenius, who worked around 1900, thought that the hydrogen ions just sit there in the water and do nothing. But we now know that's not the case. Hydrogen ions are very unstable, and what they'll do is they'll tend to react with a neighboring water. And when they do, the hydrogen ion sticks onto the water to form the hydronium ion. So really, what really goes on when you add an acid to water is that equation there. And so that's sort of a generalized equation there, where we have our acid molecule, which is HA. You add it to water, and now what you sort of have to really understand is the hydrogen ion from HA breaks off, but it just doesn't stay stable by itself. It will find a neighboring water to bind to. When it does, that water picks up that hydrogen ion and it becomes H3O, and it'll have a positive charge, and then you have the corresponding anion that's produced. Now, importantly, the H3O plus is called a hydronium ion. Okay, so really a better definition from an acid is a molecule that has a dissociable hydrogen ion or proton that produces hydronium ions. And so the person who thought of this was a fellow named Bronstead. Lowry also contributed to the theory. So this is the Bronstead-Lowry definition of acids. Again, acids are proton donors in that they donate protons or hydrogen ions to water molecules to form hydronium ions. So you need to know both definitions. You need to know the Arrhenius definition and the Bronstead-Lowry definition, which are different. Okay, so now what I want to do is to sort of reinforce this idea of the definitions of these acids is to write out equations for two acids using the Arrhenius definition and the Bronstead-Lowry definition. So first we're going to work with HCl. So I'm going to write A here for Arrhenius definition, and then I'm going to write out an equation for the Bronstead-Lowry definition. So it's going to write B-L definition. Okay. Okay, now let's go ahead and write out these equations for how hydrochloric acid dissociates in water. Okay, so we have HCl here, and so we're going to add it to water, and so it's going to produce hydrogen ions and chloride ions. And so we're going to include state symbols like I described before. Okay, so this is the Arrhenius definition of an acid. Okay, now let's look at the Bronstead-Lowry definition of the acid. So with the Bronstead-Lowry definition, you have HCl again, but this time we add water as a reactant, like this. Now the state symbol for water, it could either be L for liquid or it could be AQ for aqueous, because there'll probably be some ions in there. So either one is fine. I tend to put L. And so anyway, what happens according to the Bronstead-Lowry definition is that you see this H atom here, it breaks off and it sticks to water. And so imagine what's going to happen here is that here water is picking up a hydrogen ion proton, and so it becomes H3O, and it carries now a positive charge, so it becomes H3O, and this will be in bulk water, right? So it's an aqueous solution, and you'll get the chloride ion. So one of the things I want you to see is that with the Bronstead-Lowry definition of an acid, the acid molecule actually reacts with water to change water into a new molecule, which is hydronium, and then you get the chloride ion. With the Arrhenius definition, that is not true. HCl does not react with water. It just goes into water and dissolves in water and produces hydrogen ions and chloride ions in the water. So water is not a reactant in the Arrhenius definition. So to indicate it's not a reactant, but maybe to remind us that we have acids going into water, what I do is I put a water there over the arrow like that. Okay, so now let's go ahead and maybe look at a more complicated acid. So the complicated acid is sulfuric acid, so we're going to have the Arrhenius definition and the Bronstead-Lowry definition. So now this time we're going to look at sulfuric acid. So here is sulfuric acid, and so this is a formula you'll probably have to memorize. It's H2SO4 for sulfuric acid. And so let's write out what Arrhenius would have thought would have happened when you added this acid to water. And so if you want, you can include aqueous as a state symbol to here, although at room temperature and pressure, pure sulfuric acid is actually a liquid. So if you put an L there, that's fine, but aqueous is what most chemists do. And then what happens is the sulfuric acid, each molecule releases two of these protons here. So you get two hydrogen ions like that, and you get a sulfate ion like that. And so let me include state symbols here. Okay. All right. Now, can you write a description of how acid reacts with water according to the Bronstead-Lowry definition. Okay, so here we go. So we have sulfuric acid, and so in the Bronstead-Lowry definition, it actually reacts with water. So I'm going to write water here in the liquid state, and so this is a reactant. Now let's think about what's going to happen here, is that you're going to have two protons here, hydrogen ions, break off the sulfate and bind to two waters. So it's not so much two protons bind to one water to make this H4O+. It's really two protons bind to two different waters, making two hydroniums. So we're going to have a 2 here like that, and then we have 2 hydronium like that, and then we'll get the sulfate like that. And so if you want to, we can add state symbols to these ions here. Okay. Now, again, just to sort of remind you that the Arrhenius definition is one that you're going to have to know in class, but again, what really is thought to happen when you add an acid and water is what I'm highlighting here, the Bronstead-Lowry definition of an acid, where an acid molecule actually releases a hydrogen ion which binds to water to form hydronium and chloride. Okay, so now what I want to do is go over here and I want to talk about the definition or difference between a strong acid and a weak acid. And so we have sort of this cartoon picture here of that. And so on the left side of the cartoon picture, we have an example of a strong acid. And so here, let me just say that this could be, for example, hydrochloric acid. So I'm going to write HCl. And then on the right side of this cartoon picture, we have an example of a weak acid. And so here, maybe this is acetic acid, which is HC2H3O2. So what is the difference between a strong acid and a weak acid? It has to do with the number of acid molecules that are able to dissociate into water. So let's look at the example of the strong acid here. Let's say you have, say, 1,000 HCl molecules. When they go in the water, all 1,000 HCl molecules will dissociate, meaning 1,000 hydrogen ions will break off, stick onto 1,000 water molecules to form 1,000 hydronium ions and 1,000 chloride ions. So with strong acids, they all completely dissociate. Now, let's compare that to a weak acid. So let's say you have 1,000 acetic acid molecules and they go into water. Well, not all of the acetic acid molecules would dissociate. Instead, maybe only 2 of the molecules would dissociate. So of these 1,000 acetic acid molecules, maybe only 2 of them have hydrogen ions that break off, stick onto 2 waters, and form 2 hydronium ions and 2 acetate ions. And so when this happens, what you're left with is still mostly unreacted acetic acid. So a weak acid is an acid that does not completely dissociate in water. Maybe only 50% of the molecules dissociate, maybe only 2% of the molecules dissociate, or maybe it's even less than that. So a weak acid when added to water will not produce as many hydronium ions as a strong acid would add to water. Okay, so now what I want to do is I want to go to the board and write out chemical equations for strong acids and weak acids. And so what we're going to be doing is we're going to compare a chemical equation for one particular strong acid, which is HCl, and then the weak acid we're going to look at is going to be acetic acid, and its formula is HC2H3O2. Okay, so how do we write the equation for the strong acid? You already know how to do it. And so you imagine that you have a lot of these HCl molecules and they're going into water, and each of them will react with water, and then they will produce hydronium ions and chloride ions. Okay, so let's just step back for a moment and try to understand why is it we're writing this arrow from left to right. And so let's just imagine what the molecule population looks like before the reaction starts, and then what it looks like after the reaction is over. So I'm going to write here start and finish. Okay, so you drop the HCl into water, and right before it starts, let's say you add 1,000 HCl molecules. Now, before the reaction starts, you're not going to have any of these hydronium and chloride ions, right? But what will happen is when the reaction begins, these 1,000 HCl molecules will find 1,000 water molecules to react with them, and then the reaction will go to completion. So let's think about what we have at the end of the reaction. At the end of the reaction, all 1,000 HCl molecules have reacted with 1,000 water molecules and have produced 1,000 hydronium ions and 1,000 chloride ions. Now, do we have any HCl's and waters after the reaction is completed? No, so these are at 0. Okay, so the reason why we write a single arrow to the right here for a strong acid is because you can see that all of the reactants are going to be changed into products. Okay, now the weak acid is a little bit different. So let me go ahead and do the similar analysis for this weak acid, which is acetic acid. And so acetic acid, to some degree, will react with water. I'm going to put in the arrows in just a second, okay? But we know that the products that will form, at least to some degree, are hydronium. And then this time, we're not going to form a chloride, but we're going to form an acetate ion. So it's C2H3O2-. Okay. So now what I want to do is I want to write out what the number of molecules we have before the reaction begins, and then compare that to the number of molecules that we have after the reaction is over. So let's pretend that we add 1,000 acetic acid molecules into the solution. And so before it begins, the 1,000 molecules are there. We haven't made any hydroniums yet, and we haven't made any acetate ions yet. Now, as you know, what will happen is maybe they could react with waters. And so here, I'm just going to indicate here that maybe there are also 1,000 unreacted water molecules to start with. Okay, you know with a weak acid, that is an acid where not all of the molecules will lose protons to water to form hydronium and acetate ion. And so in the example I gave earlier, I just suggested maybe out of 1,000 molecules, only 2 of these molecules will lose protons to 2 waters to form 2 hydroniums and 2 acetate ions. So here, after the reaction is over, maybe we've only formed 2 hydroniums and 2 acetates. So what does that mean after the reaction is over? Is basically we still have 998 acetic acid molecules that are unreacted and 998 molecules of water that are unreacted. So I think you can sort of see now that we can't just use one arrow going to the right to describe how a weak acid reacts. And so instead what we do is we draw 2 arrows, one to the right and one to the left. So you might ask, well, why do we draw an arrow to the left? Well, the reason is, let's say you added more acetic acid molecules. And what will happen is you'll form more hydronium and you'll form more acetate. And then what will happen is they will start striking each other and they will reform the acetic acid and the water molecules. And so you can sort of see by that process that this reverse reaction is in play. So the reason why we use 2 arrows here is because not only do we have a forward reaction that is going on with a weak acid, but we also have a bit of a reverse reaction that's going on too. Okay, so now what I want to do is describe some strong acids versus weak acids. So one of the things you have to do in this class is you have to memorize the formulas and the names of the 6 strong acids. And so there they are. And so we have hydrochloric acid, which formula is HCl. And then we have hydrobromic acid, which is HBr. Hydroiodic acid, which is HI. Then we have 3 more acids you have to know, which are nitric acid. Its formula is HNO3. Another strong acid is perchloric acid. Its formula is HClO4. And then finally, the last acid is sulfuric acid, which is H2SO4. Now, just to point out here, these 3 acids look kind of similar. And the reason why they might is because if you look at the anions here, the chloride, bromide, and iodide, those are halogens. And so these are halogens bound to hydrogens. They're called hydrohalic acids. And these particular ones, HCl, HBr, and HI, are strong acids, meaning they completely dissociate to form ions in water. Now, let's compare that to the weak acids. And so first, a notable weak acid is another hydrogen halide, but due to the properties of the fluoride ion, it will not completely dissociate in water. So this is hydrofluoric acid. And so hydrofluoric acid has a very special place in popular culture. So you might remember the series called Breaking Bad. So that was the acid that Heisenberg used to dissolve human tissue. And it actually does that. So you want to stay away from that. Okay. Now there's some other weak acids that you need to know about. And so one that I've been sort of talking a little bit about is acetic acid. And so its formula is HC2H3O2. And then there's citric acid, and then there are many other acids which are weak acids, which I'm not going to mention here. The one thing I want you to see is that you can sort of recognize that these are all acids is because they have hydrogen as the first letter in the formula. So if you see a hydrogen as the first letter in the formula, that indicates that it's some kind of acid. You'll have to memorize which ones are strong acids, and then remember anything that is not a strong acid is considered to be a weak acid. Now, just to point out, in future classes, you will have formulas of acids, but they may not necessarily have a hydrogen in the front of the formula, but for this class, that should be the case. Okay, so we move on. So now we move on to bases. And so what I want to do is first describe what the Arrhenius definition of a base is. And so the Arrhenius definition of a base is a molecule or compound that when added to water dissociates to produce hydroxide ions. And so here what I have is sort of a generalized equation for that. And so here we imagine an ionic compound that has hydroxide. I think you see the OH there, which is hydroxide. And so the X here is the cation, is probably going to be some kind of metal. And so we have this compound that is including hydroxide. You add it to water, and then what you do is you produce hydroxide ions, and also you produce the metal cation. So that is the generalized equation for a Arrhenius base. So here are some examples. So we have one base here, it's called sodium hydroxide. It will dissolve in the water and produce sodium ions and hydroxide ions. Here's another one. We have barium hydroxide, but you can see that when it dissolves in water, each molecule of barium hydroxide will produce one barium 2+ ion and 2 hydroxide ions. Now, here's a good question to ask. We saw that with acids, that when we added hydrogen ions to water, they are unstable, and they immediately react with water to produce hydronium. Now, is that the case with hydroxide? Would hydroxide, when added to water, maybe react with water to produce something else? And the answer is no. When hydroxide goes in the water, it's stable. So as far as we know, the Arrhenius definition of a base is correct in that when you add a base, it will dissociate and produce hydroxide ions, and the hydroxide ions will just stably sit in water and not react with anything. Now, you need to know what the strong bases are. So the strong bases are listed here. They include compounds with hydroxide which are matched with group 1 metal cations such as lithium, sodium, potassium, rubidium, and cesium. These compounds are all very soluble in water, and then when they hit the water, all the hydroxide ions will break off the cations and go into the water. Now we have some other bases here, which are strong bases. They are compounds where you have a hydroxide bound to a group 2 metal. And so here, barium hydroxide, strontium hydroxide, and calcium hydroxide are all considered to be strong bases. Now just to note, barium hydroxide is considered to be a fairly soluble base, and it'll completely dissociate in water producing hydroxide ions. On the other hand, strontium hydroxide and calcium hydroxide, you may recall from the solubility rules that these two hydroxides are considered to be insoluble. We're going to correct that a little bit now. They're actually just very poorly soluble, meaning just very small amounts can dissolve in water. So it turns out that the small amounts of strontium hydroxide and calcium hydroxide that can dissolve in the water are just enough to produce just enough hydroxide ions that will make the solution basic. So now let's talk about what weak bases could be. There are some hydroxides out there that are almost practically insoluble. And so a good example of that would be aluminum hydroxide. It is very, very, very poorly soluble in water. And so it'll just release a few hydroxide ions into the water. So it really could not be considered a strong base, but it could be considered a weak base. And so this is one of the reasons why aluminum hydroxide is used as an antacid. So let's say your stomach is upset and you take some antacids, and so a lot of times they are tablets of aluminum hydroxide. And so imagine you're eating the tablet of aluminum hydroxide. The pH of your saliva and the stuff in your esophagus is neutral, and so aluminum hydroxide does not solubilize very well as it's going down your stomach. But then when it hits the stomach, because of the acidic conditions of your stomach, what will happen is the aluminum hydroxide becomes more soluble, and then it releases more hydroxide ions, which can neutralize the acid molecules in your stomach. And so that is why it's a great antacid, because you can consume it and it won't hurt you, but when it gets to your stomach, the pH is just right that it becomes more soluble, and then it releases the hydroxide ions to neutralize the acid. Now, if you were to say swallow, for example, sodium hydroxide or potassium hydroxide, those hydroxides are very soluble in neutral water conditions, and so if you ate tablets of those, what they would do is release the hydroxides in your mouth and your esophagus, which would destroy tissues, and you would have to go to the hospital. Okay, so now I want to mention that some molecules are bases not because they release hydroxide into water. And so what they do instead is that when these molecules are added to water, they will grab a hydrogen ion off water. And when you pull off one hydrogen ion off water, you are left with what? You go from H2O to HO, which is OH minus, and so you're left with hydroxide. So a perfect example of a base like this is the molecule ammonia. Ammonia's formula is NH3, and when you add NH3 or ammonia into water, what it does is that a few of these ammonia molecules here will grab protons off water, and what happens is when you have a proton or a hydrogen ion leave water and go to ammonia, which is NH3, the NH3 becomes NH4. And so this is something called ammonium cation. And so think about what is left. When you have water and you're removing a proton, you get hydroxide like that. And so here what we're doing is we're creating hydroxide in a different way. It's not being created from an ionic salt that contains hydroxide. Rather, you're having a different molecule that is accepting protons from water to create hydroxide. So this is another way to make a base. And so this way, which is applicable, is called the Bronstead method of making a base. And so this is a base that works by something called the Bronstead definition. So you may recall that the Bronstead-Lowry definition of an acid was a molecule that was a proton or hydrogen ion donor. Now what we can see is we have an example of a Bronstead base. A Bronstead base is a molecule that is a hydrogen ion or proton acceptor. Now here, just a note that when you have a population of ammonia molecules, not all of them are going to want a proton from water. And for that reason, there are not too many hydroxide ions made. If that's the case, it's going to be a weak base. And so ammonia is considered to be a weak base. So here I have sort of a final slide looking at examples of strong versus weak acids and bases. And so first off, let's take a look at this example of a strong acid. So we know that it's an acid because there's an H in the front. And we know it's a strong acid because you can see in this reaction here, we have an arrow going in one direction, so that indicates that we have a strong acid. That means is that all molecules of sulfuric acid, when they hit water, will lose protons to water to produce hydrogen ions, and here we have hydrogen sulfate. Now in this equation, what I've done is I've only written the reaction for one proton falling off the acid to form one hydronium and one hydrogen sulfate. But you could probably imagine that once this hydrogen sulfate is formed, at least some of it will lose protons and they will react with water to form hydronium and sulfate ions. Okay. Now here we have an example of a weak acid. We know it's an acid because there's hydrogen in the formula here in the front. That indicates that it's an acid. How do we know it's a weak acid? We know it's a weak acid because here the arrows between the reactants and products are going both directions. Okay, now we have some equations here of bases. We have sodium hydroxide, and it dissociates into water to produce sodium ions and hydroxide ions. Because this molecule contains hydroxide, it is a base. We know it's a strong base because we have this arrow that is going in this one direction. So finally here, what we have is ammonia. Now, ammonia is a base, and the reason why it is a base is because it's creating hydroxide ions. But here it's not so much that the ammonium itself has hydroxide. Instead, ammonia is a proton acceptor, and that hydrogen ions leave water and form the ammonium ion, NH4+, and give you hydroxide ion. And so this is a base. Now we indicate it's a weak base because we have these arrows going in both directions. Okay, thank you for listening to that presentation. We'll see you next time.